Hi, this is Kan-Lin speaking. I'm from National United University, Department of Energy Engineering. In this chapter, I'm going to talk about the material and the energy balance around fuel cell. The first section I'm going to talk about is the fuel cell test station. Because when you want to test fuel cell performance, you might need to pre-calculate the amount of fuel fit into the fuel and the exhaust composition, all those kind of conditions you need to pre-calculate. Before we introduce the test station, I'm going to discuss about what is the function of fuel cell test station or the purpose of using a fuel cell test station. The first is to try to obtain the fuel cell polarization curve. When you assemble a new fuel cell, you want to know how good the fuel cell is. So you want to evaluate the fuel cell performance. The first thing is that you want to run the fuel cell voltage against the output current. Usually, the output current higher, the cell voltage will decrease. And that depends on different kind of fuel cell. The curve might be different. Some people call this a polarization curve. Some call it the EI curve, the voltage versus current curve. From the EI curve, we are able to calculate the power. That means the voltage times the current give you the output power. So you can find out what will be the location of maximum power. That gives you indication of the fuel cell performance, how maximum power can output. From the polarization curve or the voltage versus current curve, you might be able to see different kind of characteristics. For instance, at a low current density, the voltage drop may be associated with electroactivity, and in the intermediate linear portion might be because the internal resistance. At a high current density region, the voltage drops suddenly. They may be involved some kind of mass transfer problem or the flooding. Different fuel cell, the curve might be different. For the PEM fuel cell, proton exchange membrane fuel cell, is operated at a lower current temperature, somewhere around 60 to 80 degrees Celsius. In that case, the electrokinetics, internal resistance, mass transfer all play into an important factor. So the polarization curve usually contains those three factors. For solid oxide fuel cell, SOFC, it's operated at 800 degrees, somewhere around 600 to 900 degrees Celsius. At this temperature, the electrokinetics is not a problem. The most problem will be the internal resistance, because the separator membrane actually made of ceramic. The resistance of that kind of membrane is high. So usually SOC, the polarization curve of SOC reveal those kind of behavior, internal resistance. The other purpose is to try to run the cell voltage at a constant power, constant current. So for a long time, try to see the duration or the degradation of the fuel cell. So from there, you can see for how many, for every tenth of volt, how many hours the fuel cell will last. Sometimes maybe in the intermediate also, you may try to run at a different condition, try to see the recovery rate of the fuel cell, or that you make some perturbation, say maybe shut down, slow down the oxidant or hydrogen flow rate, or reduce the current or the power output, and then come back again and see how the fuel cell responds, how fast it responds, and or had any problem for the long-term durability. For the fuel cell, we may want to know the characteristic of fuel cell and its control parameters. Usually, we can use the PEMFC as an example over here. The PEMFC called the proton exchange membrane fuel cell. Sometimes also in the early literature, somewhere in 1970s, it's called SPEFC. It's called the solid polymer electrolyte fuel cell. In the 80s, maybe also called the PEFC, polymer electrolyte fuel cell. They all talk about the same fuel cell, the fuel cell with a nephew as a separator. The fuel cell characteristics, we're going to talk about first, and then it's a control parameter, because that's parameter you need to control. So why we need a fuel cell? Because you need to control the reactant flow rate, cell temperature, and so on. So the characteristics of PEM fuel cell, the first is low voltage. For a single cell, the ideal case, the output voltage is 1.23 volt at a standard condition, pure hydrogen and pure oxygen. But in reality, on the cathode side, usually it's the air, so the oxygen concentration much lower than the pure oxygen. And then they might have a crossover and other problem. So actually operating cell voltage somewhere around 0.5 to 0.7 volt. And the second is a high current. Because for a fuel cell, if it's operated current density 1 amp per centimeter, for a small fuel cell, you can think much smaller than your hand. It's a 5 centimeter times 5 centimeter. 25 centimeter, the output of current will be 25 amp, which is much higher than the current output from the electric socket. For a commercial fuel cell, the size of the electrode may be 25 times 50. Then the fuel cell output current will be 750 amp, with the output voltage about 0.5-0.7 volt. It's much lower than a single dry cell. A single battery may be about 1.5 volt. For lithium, a single lithium battery may be 3.5 or 3.5 to 4 volt. But its output very high current. This poses a big problem because if you consider for a fuel cell, there's a load. If a fuel cell output 0.7 volt, the internal or contact resistance consumed 0.1 volt, then the load, actually the electric appliance only experience or observe a 0.6 volt cell voltage over there. It's lost more than 15% power over right there. So even with a 0.1 volt voltage loss, you need to control the resistance at a very, very low level. For instance, if you need to control voltage loss within 1.1 volt, then if the current is output current is 25 amp, then the resistance has to be lower than 4 times 10 to minus 3 ohm, 4 milli ohm, such a lower resistance. And if your output current is 750 amp, then your internal resistance or contact resistance has to control at 1.3 times 10 to minus 4 ohm, such a low resistance. Any rust or the contact area have some problem, like you will create a huge resistance, and then you need a very thick cable to reduce any contact resistance. So with this kind of current, the alligator clip, those kind of things cannot be used. And for the cell, then for the control parameters, and we consider there's a reactant flow rate, cell voltage, operating pressure, and humidity. So for a fuel cell, you need to come in air in and air out, hydrogen and hydrogen out. So the first you need to control is the reactant flow rate. You have to decide how much the air or the hydrogen had to flow in. This one you can calculate from the theoretical basis, and then from there you can set at the practical operation condition. And then the cell temperature, because for a PEM fuel cell, even different kind of fuel cell, that operate at different condition, so you need to control the cell temperature. And then the operating pressure, because you need to control the pressure, try to control the like ideal gas. So you control the pressure, you control the molar concentration. And then the humidity, because like a PEM fuel cell, the separator used is a proton exchange membrane. The membrane need to be fully hydrated in order to achieve highest ionic conductivity. So the humidification of air or even hydrogen is very important. So in order to control those kind of control parameter, people usually use the fuel cell test station to do this job. The fuel cell test station, this is a block diagram of the fuel cell test station. In the center is a fuel cell. Doesn't matter is a single cell or cell stack you want to test. And then the gas flow, you need a mass flow rate. Mass flow over here, you need to control the flow rate, but also you need to control the humidity and then the gas temperature. So you need the humidifier and then heating for the gas before it enter into the fuel cell. And on the air cathode side, the same thing. The air you have to control. You use a mass flow controller to control the air flow rate, and then also had to use a humidifier and heating to control the inlet air humidity and then temperature before it's into the cathode. And the pressure had to go through the water to go to the humidifier is go through the water pump and had a water tank inside the test station. So the gas will flow through the water tank and the bubbles through the water tank to get it fully humidified and heating purpose. And the exhaust gas, you might need to control the pressure, the back pressure. So to control certain pressure inside the fuel cell. And the exhaust gas goes through a water trap to separate the water before it's discharged into the environment. And also on the cathode side also do the same thing. And for a single cell actually need a heating because only one set of electrode inside the cell, and that had a huge area for the heat loss. But for a stack, there's a multiple cell inside. They'll generate the heat, and the heat do not have enough heat transfer area to let the heat dissipate. So actually, sometimes for kilowatt fuel cell stack, sometimes you need cooling water run through the fuel cell to remove the excessive heat. So the temperature control, not only heating but cooling, is also very important. And also the electronic load, try to measure the voltage versus current or current versus time, and you control the output power, those kind of things. Use the electronic device to control that. And then there's a discharge booster and an inverter. Depends on the fuel cell, the output power may be consumed or connect to certain kind of electric appliance. Then you need a booster or inverter to control the DC current into AC current, or the step the voltage from the low voltage to applicable voltage. Then you need a booster, inverter, or converter to do the job. This is typical, not typical, really big test station from a hydrogenic company based on Canada. Over here, the cabinet is the cell stack placed inside there, and this monitor to you can set all the control parameters, and then all the control mechanism and those control mechanisms will be underneath the cabinet. So this unit can test about 12 kilowatt fuel cell stack and much higher PEM fuel cell. For a small single cell, there's another smaller test station we can talk about at the next unit.